So the first thing we're gonna do is this is backwards of what we learned last time. We learned how to find Laplace transformations last time, and today we go backwards. So recall what we did last time. We defined the Laplace of a function f of t. We defined it to be capital F of s. The output is a function in s. And so what's going to happen here is they're going to give you f of s, and what you are required to do is to find f of t. So go backwards. And this backward process is called the inverse transform. So f of t here is the inverse Laplace of capital F of s. So in other words, in symbols you can write it like this. This is the inverse Laplace of capital F of s. That's what f of t is going to be here in this section. For example, if you remember the Laplace of 1 from last time, it's 1 over s. So if I want to go back, if I want to find the inverse Laplace of 1 over s, that would be simply 1 backwards. In general, the Laplace, inverse Laplace of n factorial over s to the n plus 1, it's t to the n. It's t to the n. And we may list all the other inverse Laplace formulas. This one was for e to the at. Inverse Laplace of k over s squared plus k squared is sine of kt. I'm assuming you really worked hard on the first section. So this is cosine kt. Inverse Laplace of k over s squared minus k squared is hyperbolic sine of kt. And inverse Laplace of s over s squared minus k squared is hyperbolic cosine of kt. And before we do further work, we need to look at linearity of Laplace inverse transformation for constants alpha and beta. The Laplace inverse of alpha f of s plus beta g of s can be rewritten as alpha Laplace inverse of f of s plus beta Laplace inverse of g of s. So now note another thing. It is possible that if the two functions f1 and f2 are not the same, and yet you still get that their Laplace the same. Their Laplace the same. Okay, so the inverse Laplace of f of s may not be unique. Just keep that in mind. Now, how about if the other way around? If their Laplace the same, are the two functions the same? Well, if the Laplace of f1 is the same as the Laplace of f2 of t, then f1, f2 are not exactly the same, are essentially the same. That's the mathematical term that we use on the interval 0 to infinity, provided that f1 and f2 are piecewise continuous functions on the interval 0 to infinity, provided t is always bigger than or equal to 0. Another note, before we start looking at some examples how to find Laplace inverse of a given function, if f1 and f2 are continuous, not piecewise continuous, just continuous, on the interval 0 to infinity, and their Laplace the same, then f1 should equal to f2 on that interval. Now, just to apply the forms we presented earlier, how do we evaluate, say, number 1, the inverse Laplace of 1 over s to the 4th? 1 over s to the 4th. So from the forms I presented earlier, we said the inverse Laplace of n factor over s to the n plus 1 equals t to the n, if you remember. So how do we get this to look like that? Well, the first thing I do is I rewrite it. This is s. 4 means 3 plus 1. This means n is 3 here. So on the top you have to have 3 factorial. But you can't just put 3 factorial there. You have to multiply by the reciprocal outside. So 1 over 6 Laplace inverse of 3 factorial over s to the 4th. If you look at this formula, it gives you t to the n, where n is 3. So 1 over 6 times t to the 3rd, or t cubed over 6. Laplace inverse of 1 over s squared plus 16. How about this? Look at the formulas and see which one fits in here. Which one does this look like? So this is going to be either sine or cosine, right? Either sine or cosine. The sine has constants on the top, no s's. Cosine has s. So this one doesn't have s on the top. So what are we going to do is we can rewrite this as s squared plus 4 squared. So in the one that doesn't have that, it says this, that the Laplace of k over s squared plus k squared is equal to sine kt. So I see k is 4, so I have to have 4 on the top. So I'm going to put a 4 here and its reciprocal outside to make it match the one on the right side. So 1/4 Now that says it should be sine kt, and k is 4. So that's what we get. Try this one. Move on. So this one, by linearity of inverse Laplace, we can break this down to 1 over s cubed, the inverse Laplace, over this one, 6 over s squared plus 4. So notice on the top there is a number, there's no s, so that reminds me of sine. But so what I'm going to do here is keep this the same for now. I need whatever here is, if it's a 3, then on the top goes 1 less than that factorial. So you have to multiply by the same thing outside. You can take the 6 out, and we have s squared plus 2 squared. So I have to have a 2 on the top. So if I put a 2 on the top, I have to put 2 outside. So that gives me 1/2. And this one, the inverse Laplace, is t squared plus, this is 3, and that's a sine 2t. Sine 2t. Number 4, inverse Laplace of 2s plus 7 divided by s squared plus 5. Plus 5. To start with this doesn't look like any of the ones we know or we are familiar with, but there's a property in algebra that says a plus or minus b over c is a over c plus or minus b over c. So we can use that to break down this function into 2 functions, or a sum of 2 functions. Then by the linearity of inverse Laplace, we can break this 2 into 2 inverse Laplaces, 7 over s squared plus 5. And let's see what we get here. That 2 that you see, you can take it outside. Inverse Laplace of s over s squared plus 5. Plus, you can take the 7 out. Inverse Laplace of 1 over s squared plus 5 as well. So the first one has s on the top. So the s reminds me of cosine. So what I'm going to do with this 5, I want to write it as something squared. That would be the square root of 5 squared. The other one doesn't have s on the top, so that reminds me of sine. So that's square root of 5 squared. And then on the top, you must have a square root of 5 to match. Okay? To match the one down there. So this one and this, they have to match. Let's see now. It's ready. So this is cosine. A is square root of 5t. This is a. This goes there. Plus 7 over square root of 5 sine square root of 5t. And that would be the answer. So that came from here. How about another example? Inverse Laplace of 2s plus 3 divided by s squared plus 3s. Oh, what is this? So if we try to split it up, I don't see s squared plus a number. I see s squared plus another s, stuff in s. So what we have to do in this case is use partial fraction decompositions. So I'm going to take this function and decompose it into a sum or difference of more than one fraction. So this one can be factored s times s plus 3. And if you remember, it's a over s, b over s plus 3. Multiply everything by the least common denominator. You get a times s plus 3 and b times s. What we need to do here is to solve for a and b. The easiest way is to set s equals 0. So you get 3 equals 3a. So from here a is 1. Set s equals negative 3. So you get negative 6 plus 3 is negative 3 equals 0 and minus 3b. Also b is 1. So I can go back to that Laplace, inverse Laplace, and rewrite that 2s, the function 2s plus 3 over s squared plus 3s as a over s, so 1 over s, b over s plus 3. And now by linearity of Laplace, inverse Laplace, you can rewrite it this way. Inverse Laplace. The plus 3, you can write it as minus negative 3. The inverse Laplace of 1 over s is s. Inverse Laplace of this is e to the negative to at, and a is negative 3. Don't forget t is bigger than or equal to 0, bigger than 0. So the partial fraction decomposition helped me to prime factorize, or to rewrite the given fraction in a prime factorization, prime decomposition form. Another example, determine the inverse Laplace transform of the function f of s, which equals to 3s squared plus 2s plus 4 divided by s plus 1 times s squared plus 4. So this type of problems takes time to do it because you want to take this one and do partial fraction decomposition. Partial fraction decomposition can take time. So first we set it up. It's in a factored form, bs plus c divided by s squared plus 4. Multiply everything by the least common denominator to get a times s squared plus 4 plus s plus 1 times bs plus c. So now what do we do next is we can select values for s. Let's say s equals negative 1, so that would give us 3 minus 2 1 plus 4 5 equals 5a. So a is 1. We can select s equals 0, so that gives 4 equals 4a, but a is found to be 1, as 0, and as 0 again, so that gives me 0 plus 1, 1 times c, so c is 0, and you can substitute s equals any value, say 1. So 3 plus 2, 5, and 4, 9 equals 5a, and a is 1, plus 2 times b, because c is 0. So subtract 5 on both sides and solve for b, so b is 2. So we got a, b, and c. Now we substitute them in and do use the inverse Laplace, linearity. So the first one looks like, if you like to rewrite it as 1 over s minus negative 1. You can take the 2 out from the top on the second one, s squared plus 2 squared. And to finish this up, this is e to the negative at, a is negative 1, plus 2, there's an s on the top, so that reminds me of cosine, and a is 2, so 2t. Again, you can write t bigger than 0. So that gives me the Laplace transform I need. One quick theorem that we rarely use here. The theorem said, as s goes to infinity, what happens to the inverse to f of s? Well, the theorem said if we let f of t be piecewise continuous function on the interval 0 to infinity, and of exponential order for t bigger than capital T, then the limit of the Laplace of f of t as s goes to infinity is the same as, or you can write it, limit as s goes to infinity of f of s is going to be 0. So the function is piecewise continuous on that interval and of exponential order for t bigger than t. Then the limit of the Laplace of f of t, which is f of s, its limit as s goes to infinity is 0. If we look at some examples, let's say given the functions f of s equals s cubed, we can take another function g of s, say 2s over s minus 1. What about these functions? If I find the limit of the first function as s goes to infinity, limit of s cubed as s goes to infinity, this is infinity. This goes to infinity. It's not 0, right? Similarly, if I find the limit of g of s as s goes to infinity, that gives us limit of 2s over s minus 1 as s goes to infinity. That's a 2. That's not 0. So this tells us that both of them, then both functions are not Laplace transform of piecewise function, continuous specifically, functions of exponential order. So it's kind of like the opposite theorem. And we can add a note to this. In this case, we can say the inverse Laplace of the first function and the inverse Laplace for the second function, both of them do not exist. Their Laplace do not exist. So it's a matter of practicing how to find inverse Laplace. That's the most important thing. We're gonna put this information we learned today with the previous section and use it for the subsequent sections starting from 7.3. Again, one thing that can happen here with this section is the partial fraction decomposition. Let's say you have 2s minus 1 over s cubed times s squared plus 9 squared, let's say, and you want to do a partial fraction decomposition. You're gonna go, this s means the whole s being cubed, so a over s, and then you do b over s squared plus c over s cubed. So because you look inside the parentheses, we have a linear factor on the inside the parentheses. That's why the tops were all constants, if you forgot about it. And the other one is s squared plus 9, because it has a power, we go 2 times until we reach the highest power, which is 2. But notice inside the parentheses here, we have quadratic in each one of them. If that's quadratic, what goes on the top is linear. It's 1 less degree wise. So that would be ds plus e, and this would be fs plus g, like that. So the setup is something that people find it difficult, but that's how it's done. And then from there are 2 ways to solve for the constants a, b, c, d all the way, is by either, after you multiply everything by the least common denominator, you can find the those numbers or those letters by either substituting into the values into the equation, values for s, as I did earlier, or you can simplify everything on the right side and left side and pairwise compare the coefficients together. That will help you to set up systems of equations. But you can use both of them at the same time to reduce the number of variables or the unknowns, if you like to do so.